Okay, so in today's lecture, which will be about 75 minutes, we will do the following. We will have a recap of the essential elements from the previous lecture, which is already uploaded online. So, both students here in person and those online can have a peek at that if you already haven't. We would have posted assignment 1. So, please make sure you have also answered assignment 1 on the NPTEL portal. If you have done both of this, then you are doing fine and you can continue with us in this lecture. So, after recapping the few things from the previous lecture, we will in this class particularly focus on the physical meaning of the solutions to the wave equation, particularly for electromagnetic waves and in 3 dimensions. And we will sort of walk into the world of superposition of electromagnetic and optical waves, and in the process learn about the some of the nitty-gritties of superpositions of light waves and apply it to a couple of cases, the more important among which would be the Fabry-Perot interferometer and Etalon. Okay, now going to the recap of the previous lecture, these are the salient aspects of the lecture we just completed. Firstly, we figured out that all wave phenomena, not just in optics, are captured in this idealized one-dimensional wave equation, where f is the scalar solution of this wave equation, and the equation itself is a linear second order differential equation. This is particularly for the case of 1D. We will graduate to more than 1D, that is up to 3D, right in this lecture, as we did as well in the previous class. So, if f is the solution for a propagating wave, then it obeys this wave equation, which is d2f by dx2 minus 1 over v square d2f by dt2 is equal to a scalar 0 on the right hand side. Here v is the speed of the wave. Okay. So, we saw this in the previous lecture. So, light waves, which are actually electromagnetic waves, and for most part, as we saw in the previous lecture, we will be talking about the electric fields of this wave, although the magnetic is just as important, is also a solution in one dimension to a similar wave equation, where v should be then the velocity of light in the medium in which the wave is propagating. It is actually the scalar component of the vectorial velocity. What do we know about the solution itself? That is the function f. In 1D, this is a function of the spatial coordinate x and the temporal coordinate t, and we showed in the previous lecture that propagating wave phenomena should be described by functions of the form f of x plus or minus v t, right. So, if the phenomenon is described by a function of this form, then this essentially captures the propagation of the wave in the so called positive x direction, or the direction of increasing x, if the function has the form x minus v t. So, v is of course positive definite, it is greater than 0, it is the magnitude of the velocity vector, and if the wave happens to propagate in the negative s x, or the direction of decreasing x, values of x, then we have the solution to be x plus v t. So, this is no error on my part. Positive direction of travel is x minus v t and negative direction of travel is x plus v t, where v is the magnitude of the velocity vector, or what we call the speed. So, as a consequence, considering the fact that this solution essentially solves this linear second order differential equation, we call the wave equation, right. F all f's which describe wave phenomena should essentially be functions which are at least twice differentiable. So, that is a mathematical requirement. Okay. So, how this f of x plus or minus v t came about. We had a sort of graphical motivation for that in the previous lecture, so you can look it up. I also emphasized in the previous lecture that this is a very this is a description of a very idealized phenomenon, in the sense that a wave scenario phenomenon or physical scene that is described by just this equation describes a wave which ideally propagates without any deformation to the wave. The amplitude of the wave remains constant in time and space forever and ever. Whatever instant of time you choose, the wave simply is a propagating phenomenon, and if it was a pulse like this, say this is the amplitude of the function f of x t at some particular time t, let us say 1 unit of time. If this is the amplitude, a description through just this equation essentially tells us that the amplitude of the wave more or less remains constant in time, okay, which is an idealization. You can imagine that there can be propagative losses to a propagating wave. Not only can there be propagative losses which decrease the amplitude of the function, there could also be other forms of deformation of this sort of a wave. The wave that began propagating like this could have gotten deformed in shape due to certain properties of the medium, such as dispersion, which we will see, which we will have a lot to discuss about in this course. Okay. So, this equation is in that sense an idealization, but it is always good in physics, science and technology to start with this very idealized scenario, because it is somewhat easy to sort of appreciate when we have a very simple propagating phenomenon. In the earlier lecture, we also looked at particular forms of functions that solve this equation, particularly periodic functions in the form of a sine or a cosine trigonometric function too, right. So, please look back at that and refresh your memory. Now, coming now to this very important edifice of modern physics and a bedrock of this course, Maxwell's equations essentially govern all of classical electromagnetic phenomena. So, all of classical electromagnetism and therefore classical optics is contained in these 4 equations, and possibly a few other relations. I would not call them equations and laws of physics on this along the same breadth, a few other equations which may be required to describe media in which these electromagnetic phenomena play out. But then we consider a particular form of Maxwell's equations in full 3-dimensional space, where the electric field is denoted by the vector E. E is a function of space and time, and the magnetic field is denoted by vector B. B is again a function of space and time. Now, if we consider these fields in a situation where there are no free sources whatsoever, that is, no free charges at all and no free currents, and keep ourselves to such a region of space, which is not the most general, but it is the playground for optics, where we essentially like to look at phenomena as playing out in a region of space and time without free sources, and if needed and on occasion when we need it, we will insert sources of these waves into the physics that we are going to look at, and then deal with them in a sort of additional manner, which will all become clear as we proceed along in this course. But if we again consider this ideal yet very useful situation where there are no free sources, that is charges or currents, then the Gauss law for the electrical part, which is divergence of E or del dot E, essentially is a 0. Divergence of B is always 0. This is the Gauss law for the magnetic part, and this is essentially due to the fact that within this framework of Maxwell's equations as I have written them, we do not consider magnetic monopoles to be existing. Anything else is beyond the purview of these very generic equations. An advanced student of physics could have considered scenarios where even this is questioned, but we are not going to do that in this course. And then we have two curl equations. The curl of E is minus dB by dt, the curl of B is mu epsilon dE by dt. So, for those who have learnt electromagnetics already, you would realize that in the equation with the curl of B, which is Ampere's law, on the right hand side we could very well have inserted a plus J sub F, as it is written often in textbooks of electrodynamics. So, that would essentially connote to a scenario where we handle free currents too, but again in this case we are not going to bother about that. We live under this assumption of no free sources. Then these four equations of Maxwell applied in this scenario essentially bring us to the wave equation through a set of simple mathematical steps. As I indicated to you in the previous lecture, consider the curl of the equation with curl of E on the left hand side, and then use the fact that divergence of E is 0 in this scenario, and with a few steps of vector calculus you would arrive at the wave equation itself, right. So, now we have the wave equation in 3D. Here please note that I have switched from using arrows on top of the fields to boldface letters to indicate vectorial quantities. So, the del square operator operating on E minus mu epsilon d2 E by dt2 is equal to the 0 vector is the wave equation in 3 dimensions. Okay. So, now if I now choose to expand del squared and choose a Cartesian frame of reference, that is a frame of reference with x, y and z, then d2e by dx2 plus d2e by dy2 plus d2e by dz2 minus mu epsilon d2e by dt2 is again equal to 0, that is the wave equation. Now, this has a solution of the form E as a function of 3 spatial Cartesian coordinates x, y, z and t is equal to E naught, the wave amplitude, the vectorial wave amplitude, multiplying the exponent of the complex exponent, which is a function of k dot r minus omega t. So, what is k dot r? K dot r is essentially in terms of this Cartesian system kxx plus kyy plus kzz, where the vector k, which is the propagation vector, has Cartesian components kx, ky and kz, and r is the position vector, and by definition this is x, y and z, this triplet. Okay. So, likewise k squared, if we so wish to take the square of the magnitude of the k vector, that is essentially k x square plus k y square plus k z square. Again, recall in the previous lecture we figured out that the magnitude of the k vector, which is k, is nothing but 2 pi divided by the wavelength of the wave. Wavelength is the spatial period of this periodic wave, and needless to say the complex exponent e to the I k dot r minus omega t has a real part plus an imaginary part. It is cosine of k dot r minus omega t plus I times sine k dot r minus omega t. So, that more or less spells out a solution for the 3-dimensional wave equation for a propagating electromagnetic wave, and here we have chosen only to describe the electric field part. Okay. So, in the previous lecture, for example, I had emphasized the concept of a phase velocity, where a point of given phase which could be a maximum over here, a positive maximum, or it could be we could have chosen a 0 crossing point where the wave amplitude goes negative, or a negative maximum, or perhaps a positive going 0 crossing. Choose any of these or any other phase point and ask the question, with what velocity does this point of a particular value in phase propagate in this case, and pop comes the answer that this is essentially the ratio of the wavelength to the time period of the wave. We discussed this in quite some elaboration in the previous lecture. So, and we also talked about the spatial period, that is wavelength, temporal period, that is the what we call tau here, and the inverse of that 1 over tau is the frequency, cyclical frequency of the wave, and if I multiply 2 pi to nu, it then becomes the angular frequency of the wave. And these two, the angular frequency omega, which is 2 pi divided by tau, and the magnitude of the k vector, which is 2 pi divided by the spatial period, the wavelength, form a ratio which is the velocity of the wave, and we can explicitly show that. This is perhaps even trivial for some of you, right. So, we have two types of wave phenomena, not necessarily talking only about electromagnetics, but the generic wave equation would have admitted both longitudinal waves and transverse waves. The direction of a wave's variations or undulations, or sometimes even called vibrations, whatever it be, essentially the direction in which the amplitude of the wave, which goes in as the f part of the wave function, right, the amplitude, essentially can, in the case of a vectorial equation, be along the propagation direction, which is like in the case of this slinky spring, the compressions and refractions, which is how sound propagates in a medium, would then be a longitudinal wave, longitude with regard to the propagation direction, and polarization is essentially the direction in which the oscillations of the wave take place. If it is parallel to the propagation vector k, then the wave is longitudinal. If on the other hand, with the same slinky, the motion which creates the transverse waves where the amplitude is perpendicular to the direction of propagation is shown here, then the wave is said to be have a transverse polarization, polarization again now being the direction in which the vibrations, variations or undulations of the wave amplitude take place. So, this holds true also for light waves, which are transverse waves. So, now we should become familiar and comfortable with the concept of vector fields as we go along. That is simply for the reason that light is essentially a three-dimensional vector field. Okay. So, what do we mean by a field? Again, for an advanced student, this is easy stuff. A vector field essentially in 3-dimensional is a function here f, but please note that f here has an arrow on top. So, it is a vector valued function, essentially has a value for this so called vector field at every point r in space, right. So, you pick a point, and then if you know how this vector field is described, you have then a vectorial value for every point in space. While 3D vector fields are hard to visualize, maybe some of you can do it with relative ease, but it is quite challenging for me to really visualize it, if at all we need it. But 2D vector fields are not that strange a concept. So, if you look at this weather map and you see, look at wind patterns, right. So, then you can pretty much follow these arrows on this wind map, which essentially tell you locally at every point what the direction of the wind velocity is. And here, in fact, the person who created this has gone a step further and color coded these vectors to also give an idea of the relative amplitudes of these vectors, right. This is a very common use thing in meteorology, and especially when the weather is turbulent, as it can sometimes be along coasts, which this city also experienced like recently. You essentially can see some very illustrative wind pattern 2D vector field maps, where a tornado or a cyclone or something like that becomes almost evident in itself. But light is a 3D vector. So, you have in general x, y, z, t in Cartesian, r, theta, phi in another coordinate system, and so on, where the electromagnetic wave has a value at every point in space, right. So, light wave essentially contains both electric and magnetic 3-dimensional vector fields, and it is again something one may have come across in earlier studies. If I now invoke a Cartesian coordinate system where I have x, y and z being the coordinate axes, and the wave propagates along the z direction, that is the k vector is parallel to the z direction. And if the green color is used to designate the electric field and the blue for the magnetic field, then essentially an electromagnetic wave propagating kind of does this, right. So, basically the electric and magnetic fields are at every instant of time and at every point in space perpendicular to each other, and they are also in phase. There is no relative phase difference between the two. That is to say that if the electric field reaches a maximum, so does the magnetic field at the same point and at the same instant of time, and the maxima are both of the same sign, that is either positive or negative. If the electric field goes to 0, the magnetic field also goes to 0. This is an essential consequence of Maxwell's equations. The wave equation is an equation independently written for E. So, it tells you how the electric field amplitude varies in space and time, whereas Maxwell's equations tell us that the electric and magnetic fields together with the vector k for the propagation form a triad. Okay. So, I am stating some of these properties without too much math and proof, because you know it, you probably know it from your earlier courses, but even otherwise, in order to keep some decent pace in this course, I would leave some of these either for a tutorial discussion or for you to even discover more of the details yourselves. For example, if you really want to convince yourselves that E, B and K form a triad, take the form of the solution that I had written down in the previous view graph, that is E, the vector E is E naught exponent of I k dot r minus omega t. Substitute this into curl of E, the Maxwell's equation with curl of E, and you will sort of with a little bit of effort figure out the fact that the electric and magnetic fields are perpendicular to each other and always in phase, right. So, now let us sort of dive into the main business of this lecture, that is to look at the physical meaning of the solutions, right. So, solutions to the wave equation. So, let us go straight into that. So, the 3D wave equation for the electric field of this vector valued equation is what we wrote down here as E, a function of x, y, z and t, with an amplitude function E sub 0. Okay. As I explained to you in the previous lecture, the tilde that we are using underneath E is to denote the fact that this is in general a complex valued quantity, that E is a E tilde E 0 E sub 0 tilde, that is a complex valued quantity. Okay. So, in the previous lecture we emphasized the fact that electric fields are real, are always real. The basis for making such a statement is that we can measure them in the physical world using instruments. Okay. So, we can only measure real valued quantities using instruments of whatever kind. So, we measure potentials, potentials are real valued, and you must have come across a formulation of electrodynamics where the potential functions play a role, play a fundamental role, and electric fields are derived quantities from that. So, perhaps an indirect sort of way to convert the directly measurable quantity into an electric field using some processing or math, right. So, electric fields are always real, please remember that. And if you want to know why, but then I have contradicted myself over here, right, writing a tilde, and I say tilde means it is complex valued. So, what is this tilde doing here? That is why I think also some of you wanted to say that this is essentially it can be complex. Yes, so this complex factor has a physical meaning, which is the burden of this current discourse, right. So, when we say that the amplitude is E naught tilde Why did this tilde come about here? So, this came about because this essentially is, and keeping to our present notation, this is essentially a real valued vectorial amplitude E naught. So, this amplitude factor also means that E naught is not dependent on space or time, it is a fixed quantity. It is this multiplied by exponent of I theta, where the vector E naught and theta are constants, or in other words independent of r and t. Okay. So, please look back into the previous lecture where we gave theta the name initial phase or even the title absolute phase. Okay. We had an interpretation for this, we discussed this extensively in the previous lecture. What this essentially means is that this form of the equation over here, that is vector E which is a function of x y z t, here essentially has E naught exponent of I k dot r minus omega t plus a theta. Okay. Now, in whatever I do subsequently using this complex notation over here, right, whatever I do with it in the math, finally I should take the real part of the E tilde vector. Okay. This is equal to E of x y z t, which is my solution. Okay. So, in that sense, this E vector is the solution to the wave equation. This E vector is this E vector, whereas E tilde is notational convenience. We will see an evidence or the importance of that even right in this lecture, the advantage of using the complex, making E complex deliberately and then realizing at the end of a discussion or an application of the concepts and math that we should only consider the real part. So, the essential solution is real, whereas E tilde is a matter of mathematical convenience. All right. So, please keep that in mind, and the reason that E naught is complex valued is because we have the initial phase 2 written down, which is the amplitude also turns out to be, we have associate a complex part with it for this reason. Okay. So, we will see more about this as we go along. Yeah. So, next, once again I keep the tilde as it is. Okay. So, E naught tilde is exponent of I k dot r minus omega t. This solution, this form of the solution where we have a harmonic solution to the equation is called a plane wave. Okay. What is so plane about this wave? A plane wave's contours are, in this case the way we have sketched it over here, field maxima. We call these wave fronts. What are wave fronts? They are actually phase fronts. And what do we mean by fronts here? By the word fronts, we essentially mean a contour. Okay. That is a collection of points which have the same value for phase. So, let us say the positive maximum. Okay. There, every 2 pi the wave attains a positive maximum after I take one of them as a reference. So, this is a point of constant phase for a cosinusoidal wave. So, if this were to be written as E naught cosine k dot r minus omega t plus theta, instead of using the imaginary exponent here, then at r is equal to 0, I am sorry about that, at r being 0 and t being 0, right, the maximum of this wave would have had a positive maximum. Okay. So, now if I go a wavelength forward in space or a period tau, time period forward in time, I would have, the wave would have replicated its wave amplitude, because this is a periodic wave. Okay. So, these 2 points are equivalent. If I go a factor lambda tau or 2 pi forward, again I reach an equivalent point in amplitude, plus 2 pi forward, plus 2 pi forward, plus 2 pi, plus 2 pi, 2 pi, and so on. All these points, right, have the same phase value. So, modulo 2 pi, they have all have the same phase value, and in this case, right, look at this plane which we have sketched over here. Throughout this plane, at a given instant of time, the value for the phase is identical. So, these are points of the same phase. Okay. And now, this propagation k, okay, has a very nice physical interpretation. Now, you can imagine this phase front, which is like a sheet of paper essentially, propagating along in a direction that is given by k, right. So, essentially the sheet of paper would, this is the phase front simply moves towards you if the k vector were to be pointing towards the audience that is sitting in front of me over here, or the audience that is viewing into the camera, right. So, k vector now has a very nice physical meaning. It is the propagation vector, it defines the direction of propagation of the wave, it is perpendicular to the wave front or the phase front. In the case of a planar wave front, at all points you can have a, you can essentially have a k vector defined at all points, any point on this wave front, and they would all be parallel. Okay. It is a matter of detail that if you had a curved wave front such as a spherical wave, you can again define propagation vectors k, where the propagation vector would at every point have been perpendicular to the wave front. I state this matter without further proof, something that you can check up on. It is not that it is very significantly important for this course, that is why we did not sort of dwell too much in it at the moment. It is for now sufficient to appreciate the fact that this is a plane wave, and the plane, that is the planar quantity, the phase front, is perpendicular to the k vector. Also note that this plane is infinite. I have put in a boundary for the sake of physical appearance around this. This phase front extends infinitely in space and actually infinitely in time too. A great idealization